Hi everyone, I'm Zhechen from Nanyang Technological University. I'm very happy to introduce our work, a practical and versatile wideband MIMO sensing platform. This work is collaborated with Tianyue Zheng and Junluo. Wireless signal is everywhere in our world. The wireless technologies have also changed our world in communication. Recently, the RF signals are further explored for sensing applications such as localization, tracking, activity recognition, and vital signs monitoring. Comparing the traditional device-based sensing approaches, RF sensing demonstrates its unique advantages of being context-free. Of course, if we want to achieve above cool applications, we need the platforms to quickly verify our null idea and then deploy it in our real life. Most sensing platforms largely depend on two kinds of devices, such as Wi-Fi cards and software-defined radio, it also called SDR. However, the Wi-Fi cards are designed for communication but not for RF sensing. In many previous research works, they always need a controlled environment. For example, a clean channel is reserved for RF sensing and the transmission settings are also quickly controlled. But in practice, clean channel connections are hard to achieve and the other parameter settings may be out of control. For the SDR, since they are special designed for flexible experiments, the hardware components are extremely expensive and unlikely to be available on commodity hardware. For example, if we want to obtain a very large bandwidth, we need to pay a high cost on the ADC chip. Therefore, we propose Octopus as a compact and programmable wideband MIMO platform for RF sensing. We implement our Octopus with inexpensive commercial-grade components. On the left side of this slide, there is a high-level architecture of our design. It contains commercial-grade UWB radio chipsets, antenna array, RF switches, ARM-based microcontrol unit, and FPGA. It not only provides a standalone mode for edge computing, but also offer raw data such as IQ signals from RF chipset to the host PC. On the right side is the image of our Octopus. Here, we give a detail of our hardware design. Our target is to design a wideband RF sensing platform, and hence the RF chipset selection is so important. In our design, after careful analysis of commercial RF chipsets, we choose UWB radar chipset with 1.5 GHz bandwidth as the basis of our design. It supports direct RF signal sampling and provides all raw data like SDR. We first look at the FPGA components on the right side, and there are several modules together to build the whole system. But the two key modules are very important in our design: the interfacing modules and the antenna board controller modules. Interfacing modules for on-chip internal and external communication. All the modules are connected via internal bus in the FPGA. We have some choices for the internal bus. For example, we use Intel FPGA, and it offers an Avalon bus for on-chip internal connection. The external CPU, such as ARM, is connected to FPGA via FMC interfaces. The antenna board controller for large-scale MIMO controlling will be introduced in the following slides. For the external ARM components on the left side, we give a logical division of codes for multiple layers. From the bottom to the top, there are driver, hardware, abstraction layer, a scheduler, and application. In our design, we only allow single application run on the platform, and we do not support multiple applications in this time. As we introduced in the last slides, the large bandwidth offers the high resolution of ranging, but the antenna array offers a good azimuth resolution. Existing antenna array architecture are divided into three major classes: digital antenna array, phase antenna array, and switch antenna array. Digital antenna array comprises multiple RF chips. Although it can achieve the best performance, but they need to synchronize all RF chips. The synchronization clock to support increasingly RF chips poses a design challenge. The phase antenna array can scan predefined direction, but the phase shifter for wideband signals is extremely expensive and very hard to manufacture. Switch antenna array is also called time division MIMO system. In this slide, we plot the switch antenna array here, and every switch introduces a considerable time delay. More antennas brings worse performance for some real-time applications. In our design, considering the pros and cons of above antenna array architecture, two-level hybrid antenna array is employed in our system. Of course, we should use amplifiers to improve the receiving and the transmitting power according to our demand. In this slide, that is the timing diagram of hybrid antenna array. It comprises a digital and switching antenna array. We can see the switching interval is much shorter than the impulse frame, and we drop the first few pulses because they are unstable during the switching interval. It is known that the two RF chips can receive the transmitting signals simultaneously in a switching cycle, and that is the advantage of our hybrid antenna array. According to previous slides about timing diagram, we design an antenna board controller for such hybrid array architecture. The antenna board controller has three components: hybrid array controller, antenna array controller, and multiple SPI controller. The hybrid array controller is used to manage the antenna array controller and the multiple SPI controller. The configuration model of the hybrid array controller received 16 parameters from the internal bus and initialized the RF chip for working. It also received the RF raw data and encapsulates them into package for up layer. The antenna switch model according to the setting parameters to set the antenna number via the antenna array controller. Then the antenna array controller toggle the GPIOs to control multiple RF switches based on predefined switching lookup table. After that, the RF signals are received by RF chips with antennas. Each RF chip connects to the FPGA using SPI interfaces. However, we find that if we use the conventional master-slave SPI bus, the throughput of multiple SPI devices decreases heavily. Therefore, we design a parallel SPI bus. We use each individual SPI bus to connect a RF chip and control multiple SPI buses simultaneously to receive RF data. Such a structure maintains a stable throughput for each RF chip. Now we present the sensing methodology for Octopus by exploiting wideband MIMO. Look at the narrowband signals. It has similar envelope sampled by the antenna array. Therefore, The narrowband signals does not have the frequency diversity. However, wideband signals such as UWB intrinsically offers a larger frequency diversity in angle parameters estimation. Since the wideband signals are time sensitivity in practice, we prefer to estimate the wideband signals parameters in time domain. Then we can jointly estimate both range and angle parameters by solving an optimization problem. We explore a general wideband sensing algorithm in completed cases, such as an unknown number of targets in the space. The basic idea of this algorithm is to back-project the receiving signals on the data plane to the target point. To illustrate this algorithm, we use one-dimension antenna array as an example, and it is easy to be extended to two-dimension antenna array. We define a data plane by receiving antenna and the fast time. Then the reflected signals from a specific target could be viewed as a hyperbola. Therefore, the reflection from the target point that is exactly located at the vertex of the hyperbola can be obtained by summing up the signals along the curve. We evaluate the performance of our system in the following slides. We evaluate the range estimation. Firstly, we obtain the range accuracy by comparing the estimated range of a solid metal block against the ground truth manually set in advance. The median range estimation error of Octopus is only 0.01 meter, and 19% of the errors are below 0.03 meter. The error also increases slightly with increasing range. The reason is the signals are much weaker in the further position. We also manually set a solid metal block at different angles. Compared with the ground truth, we get the AOA and AOD errors. We can see the AOA and AOD estimation errors of Octopus are all below 5 degrees. But the narrow signal estimation algorithms such as music are worse than us. We also evaluate different antenna elements in our system. Increasing the number of antenna elements in the array enables Octopus to increase angular resolution. When there is only one array with 8 antenna elements, the reflectors cannot be distinguished. Because the angular resolution of one array is not enough to separate signals reflected from the close-by reflectors. Fortunately, adding another array allows the reflectors to be distinguished. We evaluate the performance of localization and tracking. By combining the range and angle information, we can get the location of the target reflector. On the top left corner, the median localization error is only 0.06 meter, and the 19% of the error is below 0.2 meter. Moreover, we show the localization errors at the different ranges on the top right corner. The decreasingly accuracy in range because of the signal attenuation. Octopus is able to not only locate a target, but also keep a track of the target in motion. Target trajectory tracking can be seen as an extension of localization, as shown in the bottom of this slide. We test the AI models in our system to infer the RF sensing-based human activity recognition. We evaluate 3 different AI algorithms, such as Charge Boost, Random Forest, and CNN. The CNN performs the best in our experiments. With the help of the general sensing algorithm and the wideband MIMO resources, we also can demonstrate a higher resolution than previous Wi-Fi-based solutions. In the end, we conclude this work. Octopus is very suitable for quick implementation and verified your idea, and Octopus enabled straightforward application deployed for edge computing. Finally, Octopus can apply to many sensing applications such as localization checking, motion detection, vehicle size monitoring, and imaging. Thank you very much.